Thank you very much for letting me talk in KAIST here at Discrete math seminar today. I'll talk about mostly about permutations and affine permutations related to objects. Let's start with recalling what permutation is. So permutation, a symmetric group of bijections from a finite set to itself. And a notation I'll use is one-line notation. This means 1 goes to W1, 2 goes to W2, and goes to Wn. Okay. This symmetric group is generated by simple reflections, simple transpositions. S I will denote them by Si, and this interchanges ith and I plus first numbers of this one-line notation. Okay, this is our convention. Si interchanges the position, not the numbers. Okay. So, because since this group is generated by these simple transpositions, where I goes from 1 to n minus 1, any number, any element W in sigma n can be written as product of simple transpositions. And when this number L, which is called length of this element, is minimal, we call this a reduced decomposition. Okay. And the word A1 AL is called a reduced word. Of W. Okay. Today's topic stems out from this question. How many reduced words are there for a fixed W? And Stanley observed this interesting identity. When W0 is the longest element, longest element is m n minus 1 to 1 in one-line notation. When W0 is the longest element, the number of, I forgot to define this, but this R of W is the set of reduced words. Okay.
So do you want L to be minimal in the sense that you might have a two reduced decomposition? Yeah,
right, but there's it's a very famous property of this symmetric group that minimal number L is independent of the choice of minimal reduced decomposition. Its length is well defined. Okay, and so when W0 is the longest element, the number of reduced words of this longest element W0 is the number of standard Young tableau of shape n minus 1 minus 2 1. I'll briefly explain what this is. Okay. Shape n minus 1 n minus 1 means this tableau, this shape. And standard Young tableau is the labeling of each box of this shape so that numbers increase this way, this direction, and increase as it goes this direction. We have to put the numbers from 1 to L, where L is the number of boxes here. So L is in this case. So this is the standard Young tableau of shape n minus 1 dot 1, and Stanley observed that this number coincides with the number of reduced words of this longest element W0. This was okay. So here we can ask where this diagram comes from. What is this? Here's okay, this is for the longest element W0, but to generalize this diagram, we define the diagram of a permutation. Okay. Diagram dW of W sigma. Okay. This is the set of boxes whose coordinates are I, wj. Where I is less than j and wi is greater than wj. So this diagram actually directly encodes the inversion. Right. So here's an example. Okay. And W is 26143785. Okay, I'll first draw a dot in each boxes which corresponds to these numbers 26143785. I'll use the matrix like coordinate. So this 2 means the first row. We have the second box on the first row. But remember, this box chosen is not going to be a part of this diagram. I'll just pick a boxes first. So 2, 6, 1, 4, 3, 7, 8, 5. Okay. Now to choose these boxes from this n times n square, we have to choose certain box where a dot appears somewhere on the right of this box and a dot appears somewhere below this box. So Okay, I'll draw X here, where X in the boxes which satisfies this condition. Here's an X, here's an X, 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 here's X. Okay. Oh,
The one below the last X.
all right.
And
Here. Right. So these yellow boxes are going to be the diagram of this permutation W. When, for instance, when n equals 3 and W is the longest element, we have 3, 2, 1. And the diagram is going to be this shape, which is this. Okay. Oh. Okay. All right. So we define the diagram. We generalize this shape. Actually, what Stanley observed is more general than this. He proved that for if the diagram of a permutation is a partition shape. This partition shape up to permuting rows and columns. So this, what is partition shape? Partition shape is something can be written in this form. Partition shape means lambda 1, lambda 2, lambda r, lambda 1 is greater than equal to. So the diagram is when this shape of diagram is called partition shape, and up to permuting rows and columns means we allow permuting rows and columns of this diagram. Okay. So this is one example. Okay. So if diagram of a partition is diagram of a permutation is partition shape, then the number of reduced word of this permutation W is equal to the standard Young tabular of shape lambda. Okay, partition shape lambda. Okay. This is kind of surprising coincidence. Well, this was because it's already 20 or 30 years since this theorem appeared. And in the process of proving this theorem, Stanley actually defined a symmetric function, which is nowadays called Stanley symmetric function. That depends on this choice of permutation, and that encodes the number of reduced words of this permutation up to some rate. I won't need this definition in this talk, but I'll just write it. Okay. This looks a little bit complicated. Okay, switch that. FW of x, okay, here x means this is a former sum of infinitely many variables. Okay, x1, x2, da da da. And this is sum over all the reduced word of this W. And this is a sum of some words that satisfies this condition. These are weakly increasing, and whenever this reduced word strictly increase, this word has to strictly increase as well. And if we have these words b1 da 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 bl, we add this monomial xb1 da 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 xbl. That this function is symmetric of the permuting variables is not trivial from this definition.
So you have infinitely many variables?
Yes, we do have infinitely many variables. And symmetric means x, if we interchange xi and xj, this function doesn't change. Okay. So Stanley defined this Stanley symmetric function and proved that this is symmetric function. And since this is symmetric function, we can expand this function with very famous basis of a symmetric function called Schur function. And he proved that we can not only expand this symmetric function in terms of Schur functions, it coincides with a Schur function if W satisfies this condition. And we call a permutation that satisfies this condition. The DW is a partition shape of the permuting rows and columns. This is called vexillary. If W is vexillary. And lambda of W is the obvious partition coming from the diagram. Okay. So he proved that this FW is the Schur function when W is vexillary, and if we look at the coefficient of x1 da 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 xl of this symmetric function, from the definition, it's the number of reduced word of W. This is from the it's immediate from the definition. And on the other hand, we know that the coefficient of the Schur function of this monomial is the number of standard Young tableau. So this proves that. Okay. So Stanley found this connection between the reduced word of permutations and symmetric functions. And on the other hand, okay, and Stanley used the Stanley symmetric function. On the other hand, Edelman and Green, actually almost same year. I'll write 83, but it's almost the same year. In that paper refers to this paper, and this paper also refers to that paper. And almost the same year, Edelman and Green proved that theorem using completely different method. And when lambda is a partition, the number of standard Young tableau of shape lambda is same as number of balanced tableau they defined of shape lambda, and this is the number of reduced words if W is auxiliary. Okay, and lambda is lambda of W. So they found this another middle step called balanced tableau. And okay, so this was all the story that happened in 83, 84. And this appeared after 10 years in the work of Fomin, Green, Rayner, and Shimazana, 95. And they actually generalized the balanced tableau and connected it to Stanley symmetric function. Okay. So let's define first what the balanced labeling is. Let's say we have a diagram D. Diagram D means some collection of boxes here. Okay. Let's look at a I, j box and look at all the boxes in the diagram that are on the right side of this I, j and that are below this box I, j, and denoted hij. hij is a hook at ij. This ij, okay, and we have to first.
Hij is the cardinality.
No. It's the set of boxes here, and we first label all the boxes like we label the boxes to create standard Young tableau. We label all the boxes here with numbers and say ij is balanced if when we rearrange the numbers in the hook so that the numbers increase like this. We rearrange the numbers in the hook so that the numbers increase from right to left and from top to bottom. And when we did this, the label, the number at this I comma j remains the same. We rearranged all the numbers in the hook, but after that, when we look at this box again, the number didn't change. Then this I comma j is called balanced.
Wait, I start with the diagram
Yes,
and I put in numbers,
yes.
and this labeling, it could be balanced or not.
It could be balanced or
So it's a property of the labeling.
okay. I'll first define I comma j is balanced or not, and if every boxes in the diagram is balanced, labeling is balanced, then we call that this labeling is balanced.
Okay.
Okay. So I'll.
So the numbers are only positive integers?
Oh yes, positive integers from 1 to the number of boxes.
So all the numbers are distinct? Or
Well, okay. I'll first. If we can put any numbers, positive integers, and they can be the same in two different boxes. That's general labeling. And if a labeling is balanced and all the numbers are distinct from 1 to the number of boxes, then we call it injective balanced labeling. Okay. And column strict balanced labeling is a balanced labeling that if we look at each column, the numbers appearing in the column are all distinct. Injective balanced labeling has to contain only the numbers from 1 to number of boxes, but column strict balanced labeling doesn't have to. Okay. So, and the theorem is this. Let W be in the symmetric group, and then the Stanley symmetric function is a number. It is summation of these monomials xt, where t is a column strict balanced labeling of the diagram of W, and xt means is the monomial that is the product of xi's to the power of number of i's appearing in the labeling T. Okay. So this summation ranges over all the column strict balanced labelings of this diagram, and we add all the monomials appearing in this labeling, we get Stanley symmetric function. So corollary of this theorem says that the number of reduced word of this W equals the number of injective balanced labelings of this diagram, because this is the coefficient of monomial x1 xl. Okay. So, I'll show you a very tiny example. This W is 3 to 1 in sigma 3. Then it's the longest element in sigma 3, and there are two reduced words of this W. Okay, S1, S2, S1, S2, S1, S2, and there are two balanced labellings. I mean, injective balanced labellings. These are balanced because 1 and 3 are obviously well balanced, and 2, if we rearrange the numbers appearing in this hook, it becomes 1, 2, 3, and 2 doesn't change. So 2 is also balanced in this case. This is balanced, and this is also balanced. And if we remember the previous theorem of Stanley, this equals the number of standard Young tableau as well. There are two standard Young tableaus of this shape, and two injective balanced labellings of this shape. But in this case, it feels like it's going to be easy to find the bijection between this Young tableau and balanced labeling. But for general permutation W, it's not known. The bijection hasn't been found.
But in the staircase shape, it's not.
Yeah, for partition shape, it's
For
known.
partition shape.
Yes. Okay. Now we talk about affine permutations. Affine permutation is an affine extension of symmetric, finite symmetric group. So it's a group. It's a group of bijections that goes from integer to integer. And this is generated by simple transpositions. And as I interchanges I and I plus first modulo m positions. And W is okay. It's a bijection from Z to Z, so it can be realized as an infinite sequence of integers. Like, say the identity element is going to be like this, and say S0. Okay, here I goes from 0 to n minus 1. Okay. S0 interchanges is, okay, let's say n equals 3. Okay. We are looking at sigma 3 tilde. Then S0 interchanges 0 and 1, 3 and 5, and -3 and -2, and so on. So S0 is going to be -4, -2, -3, -1, 1, 1, 0, 2, 4, 3, Okay. and S0, S1 interchanges this and this and this. So S0, S1 is going to be -2, -1, -3, 1, 2, 0, 4. Okay. And the window notation of an affine permutation is just looking at this part, because this n numbers completely determines all the sequence, because it's periodic. We can only look at these numbers, and looking at these n numbers are called window notation of this affine permutation. Okay. All right. Then we can ask how many reduced words are there for affine permutations. So we can ask very similar questions that we have seen before. Okay.
So,
Yeah.
wondering, so is it S0, S1 or S1, S0?
S0, S1, it's convention. Okay. You can just, yeah. You can just
So you
say
multiply from the...
from the right, yeah. Because we interchange these positions, we are multiplying from the right. Okay. Recently, well, I'm not sure if we can say recently it's 06, but Thomas Lam defined affine Stanley symmetric group, affine Stanley symmetric function. Tilde x for all w affine symmetric group. I won't give you a definition of affine Stanley symmetric function because it needs many new concepts, new definitions to be explained. But I'll just say that this is a very nice affine counterpart of classical finite Stanley symmetric function. So, for example, if W is contains a finite symmetric group, okay, this affine symmetric group contains finite symmetric group. We can just look at the subgroup generated by S1 Sn minus 1. You can ignore S0. Then this window notation just becomes the one-line notation. Okay, and when W is in that finite symmetric group, then this affine symmetric function just becomes the Stanley symmetric function, obviously. And the coefficient of x1 xl is the number of reduced words of this W affine permutation. And we know that Stanley symmetric function is sure positive. Okay, I didn't explain what this is, but it means this is a symmetric function, so you can expand in terms of sure functions. And in that case, every coefficient appearing in that expansion is positive integer. And F tilde W is something called affine sure positive. It's not sure positive, but it's Hwanchul positive. And say, as I said before, this is the Schur function. If W is something called Grassmannian permutation. I didn't explain what this is, but when W is something called Grassmannian permutation, this Stanley symmetric function becomes the Schur function, and this is a affine Stanley symmetric function becomes a affine Schur function, if W is affine Grassmannian. Well, in some sense, this is the definition of a affine Schur function, but I'll say that this is a property. As Schur functions form a basis of symmetric functions, a affine Schur function forms a basis of this space of symmetric functions that contains this affine Stanley symmetric function. And many more properties like FW Stanley symmetric function is geometrically related to the spread calculus of Grassmannian and Flag variety. On the other hand, affine Stanley symmetric function is geometrically related to affine Flag variety and affine Grassmannians, which are much more complicated than Flag varieties and Grassmannians, because affine Flag varieties and affine Grassmannians are not algebraic varieties. They're in the schemes. Like it's much more complicated, but it's this function, this combinatorial defined function, is very deeply related to that geometry. Okay. And yeah. Right. So we can try to define the diagram of affine permutation. In this case, the definition is almost exactly the same as the diagram of a finite permutation. But in this case, we have infinitely many WIs. It's an infinite sequence. So it's contained in Z times Z. So it's infinite collection of boxes. And I'll show you an example. Okay, this is a window notation of affine permutation in sigma 3 tilde. This is like actually 1, -1, -3, 4, 2, 0, 7, 5, 3. Okay. Then we just do a very similar thing as in the finite case. We have 4, 2, 0. So 4, 2, 0, and 7, 5, 3, and here -3, 0, -3. -1 and 1. I'll replace the dots, and define the boxes as before. Like this. So it's a periodic collection of infinitely many boxes. Okay. But we can, since that's periodic, obviously we can just identify all the boxes in the same period. So we can just look at this as a finite number of boxes on a cylinder. We identify I comma j and I comma n, I plus n comma j plus n. Then this becomes a collection of boxes on a cylinder, and it's a number of boxes are finite. It is finite, and we can define a labeling as a labeling of the boxes on the cylinder, and we can define balanced labeling, injective balanced labeling, and column strict balanced labeling in the very same way. You can just I'll give you later an example. Let's first state our theorem. Okay. The affine Stanley symmetric function is the summation of monomials. This is a very predictable theorem. Well, the sum is over all the column strict balanced labelings of this affine diagram. Okay. So corollary, as a corollary, we have that the number of reduced words of this affine permutation is the same as the number of injective balanced labeling of this diagram. Okay. Actually, we have a more direct bijection. We have a bijection from the injective balanced labelings to the reduced words of affine permutation. I'll briefly describe. Is a bijection. I'll define psi in an example. So I'll use that diagram. Yes. This is an example of injective balanced labeling of that diagram. Okay. This is obviously the labeling of the diagram, and every boxes are balanced. For example, 3 is balanced because if we look at this hook and rearrange the numbers, then it becomes 1, 2, 3, 4, and 3 didn't change. And all the other boxes are balanced. So this is the injective balanced labeling, and I'll right here. Since there are 4 boxes, we write 1, 2, 3, 4 on this table, and we will enumerate some numbers for each box. This I means a row index.
So I want to try to understand. So if I interchange 4 and 1, then it is not balanced anymore, right?
Right. Because in that case, this becomes 4. Then if we look at this hook, 4 is bigger than it. Right. So, okay, I is the row index of the number where the of the box where the number appears. So 1 for 1 is here, and this is the first row, right? This is the first, second, this is 0. Okay. So we write 1 here. 2 is on the second row. 3 and 4 are on the first row. So this is 1, 2, and 1. And R plus is the number of boxes on the same row which are greater than this box. So for 1, there are 2 boxes. So this is 2. For 2, there are no boxes. 3, there's 1 box. 4, there's 0 box. And U plus is the number of boxes above this box which are greater than this box. So for 1, there's no box. For 2, there's 1 box which is greater than 2. And for 3 and 4, there are no boxes greater than this. And we will put negative on this U plus and add all the numbers. And this becomes 3, 1, 2, 1. And we mod out by n. In this case, mode 3. This becomes 0, 1, 2, 1. Okay. And this 0, 1, 2, 1 is the reduced word corresponding to this labeling. So this labeling corresponds to S0, S1, S2, S1. In sigma 3 tilde, this is 4 to 0. Actually. Okay. And we can prove that this correspondence is the bijection. Okay.
Can you repeat the definition of the balance?
Oh, balanced? Okay.
So whenever you rearrange so that it's in increasing order?
So in this hook of I, j, we rearrange all the numbers in here so that it increase from right to left and increase from top to bottom.
Right, so if
Right.
you rearrange like that, and then numbers doesn't...
Yeah, after this rearrangement, the number at ij doesn't change, then this ij is balanced. And if every boxes in this diagram are balanced, this diagram is called balanced.
Yeah, so for instance, if I rearrange along this hook,
Yes,
then...
then it becomes 1, 2, 3.
Oh, I see.
Yeah,
This
and
way, okay.
yes, 1 didn't change.
All right.
Yes. So, okay. So, yeah. And if we remember this construction of reduced word from a balanced labeling, we can find one very easy reduced word coming from a very easy balanced labeling. I mean very easy by this. So if we have a diagram, we just look at one period and we write down numbers from 1 to the number of boxes from top to bottom each column, and each column moves from right to left. then this makes a very obviously this makes a balanced labeling. And we call this oriental balanced labeling because this writing and reading order is traditional way of writing and reading in these East Asian countries. Oriental labeling. Okay, and if we look at this oriental labeling, this U plus is always 0 because numbers increase in this way everywhere. So we can ignore this U plus, and if we write write down the number I plus R plus in each box, we get some interesting numbering. I will not call this labeling because we used labeling for a different concept, but numbering of boxes. For example, in the same example I was using, this becomes 1, 2, 3, 2, 4, 5, 5, 6. Here's 0, negative 1, negative 2, negative 1, so on. Okay. So we didn't load out by n. And then, if we look at this numbering, it has a very nice property. It consecutively increases on each row and column everywhere, 3, 4, 5, 1, 2, 3, like this. And if we have two boxes like this, then and numbers are alpha and beta, then beta minus alpha is always greater than equal to 2. This can be proven. And we call this some numbering that satisfies these two conditions, consecutively increase on each row and column, and that satisfies this condition. We call this numbering a content of the diagram. Okay. A content of a diagram is, I won't write down, but it's a numbering of boxes that satisfies these two conditions. And we prove that a periodic collection of boxes in Z times Z is a diagram of affine permutation for some W n periodics. Okay. If and only if it is it satisfies this northwest property and there exists a content map. Northwest property means if we have these two boxes in a diagram, we also have to have this box in the diagram. If it is a northwest property, it satisfies northwest property and there exists a content map, it is a diagram of affine permutation. It's a necessary and sufficient condition. Okay, since we are out of time, I'll stop here. Maybe I can just finish with some questions. Happy first. Questions. As I said, there is no. Yeah, n periodic. N periodic. And this is sigma n tilde. Right. And so as I said before, there's no bijection found for for wait a sec. No. I didn't explain something, so but okay. If we have two permutations of affine permutations that satisfies, I mean that have the same affine Stanley symmetric function, then we know that the number of reduced rows are the same. Is there a canonical or very nice bijection impose this condition? The affine Stanley symmetric functions are the same under the same conditions, and we ask, is there a nice bijection between injective balance labellings of these diagrams in that case? And this is not known for even finite permutations. And one very special example is the bijection between standard Young topology of partition and balanced labeling, injective balanced labeling of the same partition. But for other diagrams, it is not known. This is the most interesting question I have in mind for now in this direction. And yes, I'll stop here.